We're now going to look at the three types of collisions: elastic, inelastic, and recoil. We're going to be taking a look at the law of conservation of momentum and how we can use that law to find information about the speed or mass of an object before or after a collision. Now, remember that we touched on them briefly in a different video. Elastic means start separate, end separate. So elastic, we start separate and we end separate. Inelastic, start separate, end together, and recoil. Start together and end separate. So let's go ahead and take a look at some collisions. We're going to begin with elastic collisions, which were start separate, end separate. Now you can see there is an equation that can be used for all elastic collisions. What I'd like to do instead is take a look at it using a more visual approach, something I like to call the box method. So essentially, we're going to draw boxes to represent the objects that will be involved in the collision. Inside of the box, we're going to be putting the mass in kilograms. And above the box, we're going to be putting the velocity in meters per second. Now you'll see the left-hand side is before the collision. The right-hand side is after the collision. So the law of conservation of momentum says that the total momentum before the collision has to equal the total momentum after the collision. You'll recall that momentum is the product of mass and velocity. So if I want to find the momentum of this 2 kilogram object, I have to multiply its mass times its velocity. So 2 times 8 is 16 kilogram meters per second, plus 4 times 2 is 8 kilogram meters per second. That has to equal the total momentum after the collision. So this is going to be 2 kilograms times 0, which is going to be 0 kilogram meters per second, plus 4 kilograms times some unknown velocity. So if I add up my total momentum before the collision, it looks like I'm going to get 24 kilogram meters per second. 0 plus 4 kilograms VF is going to be 4 kilograms VF. And you can see that if we divide both sides by 4 kilograms, we are going to get VF is equal to 6 meters per second. So again, the law of conservation of momentum says the total momentum on the left-hand side has to equal the total momentum of the right-hand side. So the total momentum before the collision has to equal the total momentum after the collision. Let's go ahead and try another example. And you'll notice this one is really going to have two objects moving in different directions. We'll put arrow vectors on top to indicate the direction of the objects. So this one is positive 6 meters per second for the 4 kilogram object, so we're going to say that's right. We have negative 2 meters per second for the 6 kilogram object. So to find the total initial momentum, I have 4 kilograms times 6, which is 24 kilogram meters per second, plus I have 6 times negative 2. So that's actually going to be minus 12 kilogram meters per second equals 4 times negative 3.6, which is going to end up being negative 14.4 kilogram meters per second plus 6 VF. So again, we're trying to find that final velocity. So when I do that, if I add up my total initial momentum, you'll notice because one was right, it was positive, one was negative, it was left. So when I add them together, I'm actually just going to get plus 12 kilogram meters per second, and that has to equal negative 14.4 kilogram meters per second plus 6 VF. So I have to add 14.4 to both sides. Which is going to give me positive 26.4 kilogram meters per second equals 6 VF. When I divide by 6, we get VF is equal to 4.4 meters per second. So as you can see, the law of conservation momentum just says the total momentum before has to equal the total momentum afterwards. Go ahead and try practice problems 3 and 4 for elastic collisions. So for number 3, you should have got the initial velocity of the 8 kilogram mass was 0, so it was at rest initially. And then for number 10, you should have gotten the initial velocity of the 8 kilogram mass was 8 meters per second. So that's elastic collisions. Let's go ahead and take a look at inelastic collisions. Okay, you can see that inelastic collisions are where the objects start together and end separate. Again, there is an equation that can be used, but I find students have more success if they use this box method because it forces them in a way to visualize the collision. The law of conservation of momentum is the same. The total momentum before has to equal the total momentum after. So let's take a look at this first example. So we have a 2 kilogram mass moving at 10 meters per second, an 8 kilogram mass that's at rest. After the collision, they're going to stick together, and we want to figure out their final velocity after the collision while they're moving together. So in order to do that, we have to find our total initial momentum. So my 2 kilogram mass was moving at 10 meters per second. So 2 times 10 is 20. So that's going to give me a positive 20 kilogram meters per second. Plus 8 times 0, this is just going to be 0 kilogram meters per second. Because if the velocity is 0, the momentum is 0. If there's no mass in motion, there is no momentum. Law of conservation of momentum says I have to set that equal to the momentum after the collision. So the 2 kilogram mass and the 8 kilogram mass are going to stick together and move as one object. So they're going to be acting as one 10 kilogram mass moving at some unknown velocity. So you can see that I've added 2 kilograms plus 8 kilograms to get 10 kilograms because their total mass is going to be the sum of the two individual parts. So let's go ahead and finish solving that. So I get 20 kilogram meters per second equals 10 kilograms. Times the unknown final velocity. And you'll see if we divide 20 kilogram meters per second by 10 kilograms, we're going to end up with a final velocity of 2 meters per second. So that means the two objects, the 2 kilogram mass and the 8 kilogram mass, will be moving together as one 10 kilogram mass with a velocity of positive 2 meters per second. Let's try another example. So initially here in number 2, I have an 8 kilogram mass moving at positive 5 meters per second. So that object's going to be moving to the right. We have a 6 kilogram mass moving to the left at 2 meters per second, or a velocity of negative 2 meters per second. And then that has to equal the total momentum of a 14 kilogram mass moving at some unknown final velocity. So let's go ahead and set this up. So 8 times 5 is 40 kilogram meters per second, plus 6 times negative 2 is negative 12 kilogram meters per second. So by adding those together, that gives us the total initial momentum. We're going to set that equal to the total final momentum. 8 plus 6 kilograms is going to be a total of 14 kilograms times an unknown final velocity. So we have 40 plus negative 12. Looks like we're going to have a positive 28 kilogram meters per second equal to 14 kilograms times our unknown final velocity. So 28 kilogram meters per second divided by 14 kilograms is going to give me a final velocity of 2 meters per second positive, which indicates that the two objects will be moving together to the right as one 14 kilogram mass. Go ahead and finish number 3 and number 4 on your own. So now that you've finished them, you should see that the initial velocity of the 5 kilogram mass was 3 meters per second left, or negative 3 meters per second. And in number 4, the initial velocity of the 5 kilogram mass was 8 meters per second left, or negative 8 meters per second. So we've now taken a look at elastic, start separate, end separate. We've taken a look at inelastic, start separate, end together. And now we're going to take a look at recoil. So recoil was start together, end separate. So you can think about that as the opposite of inelastic, if that helps. You'll see that I'm still using the box method to help me visualize the collision. So let's take a look at this. So this is a recoil collision. We're starting together, ending separate. So we have a 4 kilogram mass and a 6 kilogram mass that are together. So initially they're acting as one 10 kilogram mass traveling at 0 meters per second. And afterwards, after they separate, after the collision, we're going to have a 4 kilogram mass moving at negative 3 meters per second. So 4 times negative 3 is negative 12 kilogram meters per second, plus the 6 kilogram mass is traveling at some unknown velocity, so that's what we're looking for. So we're going to write that as 6 kilograms times Vf, the unknown final velocity. 10 times 0 is just 0, equals negative 12 kilogram meters per second, plus 6 kilogram Vf. Add 12 kilogram meters per second to both sides. If I divide both sides by 6 kilograms, you can see I'm going to get a Vf of positive 2 meters per second, which means that this 6 kilogram mass is going to be moving to the right at 2 meters per second after the collision. All right, so let's take a look at another example here. Number 2, initially we have a 10 kilogram mass because we have the 4 and the 6, which are together, traveling at 2 meters per second. And that's it for total momentum because they're stuck together. And then afterwards, the 4 kilogram mass is moving at negative 3 meters per second, or 3 meters per second left. So I'm going to get negative 12 kilogram meters per second plus 6 kilograms times an unknown final velocity for the 6 kilogram mass. So our total initial momentum, 10 times 2, is going to be 20 kilogram meters per second equals negative 12 kilogram meters per second plus 6 kilograms times the unknown final velocity. I have to add 12 kilogram meters per second to both sides for a total of 32 kilogram meters per second equals 6 kilograms times the unknown final velocity. So I have to divide both sides by 6 kilograms. And when I do that, I'm going to get a final velocity. I'm going to get a final velocity of positive 5.33 meters per second. That tells me that the 6 kilogram mass will be moving right at 5.33 meters per second after the collision. So this is the third type of collision now. We've gone over elastic, start separate, end separate, inelastic, start separate, end together, and now recoil, start together, end separate. Go ahead and finish practice problems 3 and 4. And once you've done that, you should see that the 8 kilogram mass was initially moving, or after the collision will be moving left at 3 meters per second. And in practice problem number 4, the 2 kilogram mass will be moving left at 14 meters per second. So now that we've introduced the box method, we can go ahead and take a look at some application problems. So this is more representative of a problem you would get on a quiz or a test. So the first thing you're going to do when you read the scenario is you have to decide what type of collision it is. Then you're going to set up your boxes. We'll label it based on the given information, and then we'll go ahead and solve it just like we did on the 3 practice pages we've already done. So, a 75 kilogram goalie at rest stops a 105-gram hockey puck. We'll have to make sure we put that in the correct units. From a speed of 48 meters per second. Find the speed the goalie slides on the ice with the puck. So, initially we have the puck and the goalie. So, we're going to have to figure out the total initial momentum by looking at both of them. So the goalie had a mass of 75 kilograms, and the goalie was initially at rest. The puck had a mass of 105 grams, but we have to convert that to kilograms, so that's 0.105 kilograms. And it was moving at 48 meters per second. Afterwards, the goalie's going to slide back with the puck. So they're going to be ending this collision together. So the 75 kilogram goalie and the 105 gram or 0.105 kilogram puck will have a combined mass of 75.105 kilograms as they move together at some unknown final velocity, which is what we're trying to find. So let's go ahead and set this up. We're going to have to multiply the mass times the velocity, just like we did in the practice problems. So we have 0.105 times 48 plus 75 times 0, which is just going to be 0, equals 75.105, because now they're together, times the unknown final velocity. So when I multiply 0.105 times 48, I get 5.04 kilogram meters per second plus 0 equals 75.105 VF. So I'm going to go ahead and solve. I have 5.04 kilogram meters per second equals 75.105 kilograms VF. So we're going to divide both sides by 75.105. And when we do that, we're going to get a final velocity of 0.06711. We'll just leave it as 0.067 meters per second. Now the total initial momentum was positive, so the total final momentum is positive. So it's going to be moving at 0.067 meters per second. In this case, we'll say to the right after the collision. Okay, number 2 is a specific application. It's typically called the ballistic pendulum, but we'll just take a look at it in terms of conservation of momentum. So I have a 35-gram bullet. Remember, I have to divide by 1,000. So 35 divided by 1,000 is going to be 0.035. Kilogram bullet is going to hit a 5-kilogram block, and then they're going to slide backward together. So again, starting separate, ending together. So I have 0.035 kilograms for the bullet. Traveling at some unknown initial velocity. Plus, we have just a 5-kilogram block, which is at rest on the table. The bullet's going to be fired into this block. And then after the collision, the bullet is going to be embedded in the block and they'll be moving back together. So they'll be ending together, in which case they'll be acting as one 5.035 kilogram object. And it tells me that they're going to be moving back together at a final velocity of 8.6 meters per second. So our goal is going to be to find the initial speed of the bullet, or the initial velocity. So we're going to set up our equation. So mass times velocity, so we have 0.035 times VI, plus 5 times 0, which is just 0, equals, we have to multiply 5.035 times 8.6. And when we do that, we get 43.301 kilogram meters per second. So I know that the 0.035 VI is equal to 43.3 kilogram meters per second. So I have to divide both sides by the 0.035 kilograms. So 43.3 divided by 0.035 is going to give me an initial velocity of 1,237.17. We'll just leave it like this. So that the initial speed of the bullet in scenario problem number 2 is 1,237 meters per second. Now let's take a look at number 3. A 35-gram bullet hits a stationary block at 475 meters per second and exits the block at 275 meters per second. Notice it says exits the block. So they're not going to be together after this collision. Now we're going to find the speed of the block after the collision. So if you think about it, they were separate in the beginning. They're going to be separate in the end. So this is for an example of an elastic collision for our purposes. So 0.035 kilograms is the mass of the bullet. It's initially moving at 475 meters per second. We also have a block, which is a 2.5 kilogram block in this problem, was stationary, which is another word for at rest, equals, and then after the collision, we're going to have the block, which will be moving at some unknown speed, we'll write Vf, and we're told that the bullet, which had a mass of 0.035 kilograms, continues moving at 275 meters per second after passing through the block. So we plug that into our calculator, and we get 0.035 kilograms times 475 is 16.625 kilogram meters per second, plus 2.5 kilograms times 0 is 0 kilogram meters per second, equals 2.5 times the unknown final velocity of the wooden block, plus 0.035 kilograms times 275 meters per second is 9.625 kilogram meters per second. So we have to subtract the 9.625 over, and we get 7 kilogram meters per second equals 2.5 kilograms times final velocity. So we have to divide both sides now by 2.5, and we'll see that we have a final velocity of positive 2.8 meters per second. So after this collision, the block, the 2.5 kilogram mass, will be moving at 2.8 meters per second. So we go ahead and read the next one. We have a 0.5 kilogram ball traveling at 6 meters per second, strikes a 1 kilogram ball moving at negative 12 meters per second. The 0.5 kilogram ball moves away at negative 14 meters per second after the collision. Find the speed of the 1 kilogram ball. So let's go ahead and draw everything we know. We have a 0.5 kilogram ball in the beginning, and we have a 1 kilogram ball in the beginning. And the 0.5 kilogram ball is traveling at plus 6 meters per second. The 1 kilogram ball is traveling at negative 12 meters per second. So that's the initial. At the end, it tells me the 0.5 kilogram ball is moving at negative 14 meters per second. And I want to find the speed of the 1 kilogram ball after the collision. So that's what we're looking for. Now you can tell based on context, I've identified this as an elastic collision, starting separate, ending separate. And so it's just going to be a matter of finding the momentum of each piece and setting the total initial momentum before equal the total momentum after the collision. So 0.5 times 6, that's going to be 3 kilogram meters per second, plus negative 12 kilogram meters per second, equals negative 7 kilogram meters per second, plus 1 kilogram Vf. So we combine like terms here, we're going to get negative 9 kilogram meters per second as total initial momentum equals negative 7 kilogram meters per second plus 1 kilogram Vf. Add 7 to both sides, we get negative 2 kilogram meters per second equals 1 kilogram Vf. And divide both sides by 1, and you're going to get the final velocity of the 1 kilogram mass is going to be negative 2 meters per second, or 2 meters per second left. So initially they were moving this way, Afterwards, after their bounce, they're moving away from each other. So we've now gone over an application of inelastic. We've gone over an application of elastic. Let's take a look at some recoil scenarios. So initially we have a 4 kilogram rocket in space. So I'm just going to write 4 kilograms. And I'm told that it's at rest. So our speed is equal to 0. So that's it for before the collision. The total initial momentum is 4 times 0, or 0 kilogram meters per second. It then tells me the rocket fires 50 grams of mass, with a reminder here to make sure it's in kilograms. So afterwards, we're going to have the gas, the fuel, which is going to be 0.05 kilograms. And then we're going to have what's left of the rocket, which is 4 minus 0.05 or 3.95 kilograms. Because the fuel is initially part of the rocket. So if the rocket gets rid of some fuel, okay, it's gotten rid of some mass. So if I start out with 4 kilograms and I get rid of some mass, my mass has to be now less than the initial 4 kilograms. And so I did the 4 kilograms minus the mass of the fuel that it has gotten rid of. Now it tells me that that fuel was fired out of the rocket. In this case, we'll assume leftward, negative 625 meters per second. And it's our goal to figure out what velocity did the rocket get by throwing the fuel out at 625 meters per second. So 0 equals, so I have to do 0.05 times the negative 625 plus 3.95 VF. So if I do that, I get negative 31.25 kilogram meters per second plus 3.95 VF is equal to 0. So add 31.25 to both sides. So 31.25 kilogram meters per second equals 3.95 VF. In order to find that final velocity of the rocket after we've gotten rid of the gas, you have to do 31.25 divided by 3.95, and that gives us a final velocity of positive 7.91 meters per second. So it'll be going to the right. And that should make sense. If my total initial momentum is 0, okay, and I throw the gas to the left, the rocket's going to have to be moving to the right because we still want to add to 0 for our total final momentum. So this is our first example of a recoil problem. Let's take a look at another. Okay, we have another example here of a recoil collision. So we have a 1.5 kilogram cart and a 4.5 kilogram cart that are initially right next to each other. And so when they're connected, their combined mass is going to be 6 kilograms. And they're at rest, so their initial velocity is 0. The student presses the button, and the two carts are then going to be driven apart. So at that point, we'll have a 1.5 kilogram cart, and we'll have a 4.5 kilogram cart that are separate. It tells me that the 1.5 kilogram cart is moving left at 0.27 meters per second, and the 4.5 kilogram cart is going to be moving at some unknown speed, VF. Well, as you can see, the total initial momentum is 6 kilograms times 0 meters per second. So 0 is the total initial momentum. I then have to multiply the 1.5 kilograms times the negative 0.27, which will give me negative 0.405 kilogram meters per second plus 4.5 VF. So again, this whole thing was 0. So I'm going to move the negative 0.405 kilograms over, so I'll get positive 0.405 kilogram meters per second is equal to 4.5 times final velocity. And I now have to divide both sides by 4.5 kilograms to figure out that final velocity. When I do that, I get positive 0.09 meters per second, in which case the 4.5 kilogram car is going to be moving right at 0.09 meters per second. Okay, so at this point, we've had 2 examples of elastic collisions, 2 examples of inelastic collisions, and now 2 examples of recoil collisions. So hopefully you find this box method a useful tool to force you to read the scenario, interpret the scenario, identify the type of collision, and then find the initial or final velocity that you're asked to find. So that is the 3 types of collisions and the applications of conservation of momentum.